Thank you very much for the introduction, and thank you very much for the opportunity to be able to speak here a little bit about my job as an enforcer of food contact material legislation. So if you feel that food contact materials or the consumers are not protected adequately from food contact material, feel free to blame me, because I do have part of the blame for this. But I'm not so arrogant as to claim the full blame for it. So my job on the surface of it is quite easy. You check if something gets from the food packaging material or food contact material into the food, then you analyze it, and if it exceeds a limit, you take it off the market. If it's not, you go to the next food contact material and analyze it. So it sounds quite easy, and for many aspects of food safety it is so easy because there are very well established microbiological limits for food and for hygiene. And so you can just do exactly these 3 steps. So I've highlighted some of these words in red, and I would like to speak about these in turn. So the first thing is the something. So chemists, when they speak about something, they speak about chemical substances usually. This is the scale at which chemists think. They think in chemical substances. And I have given you an example here, and it's arguably one of the most important substances, especially for conferences. It's caffeine. But this is a picture of a substance, and there are many. I'm not sure how many of you are not chemists, but there are millions and millions and millions of them. The universe in chemistry is absolutely enormous. And there are a few important things I would like to highlight about substances. And the first thing is that they react. This is the heart of chemistry. Substances react and they turn into something else. And those of you who have flown here from the States, they will have burnt a lot of petrol or fuel in the airplane. And after this fuel is burnt, there is no more fuel. It is something completely different, and it has completely different properties. This is very important to note, as we will see later on. It seems quite trivial, but I nevertheless thought it was good to state very clearly. Then, substances have properties. They have melting points, they have boiling points. And one of the properties they have is related to toxicity. I'm not a toxicologist, so it's a whole branch of science, the toxicity of substances. But there are some things that I can understand, and I would like to tell you. There is a hazard, which is an intrinsic property of a substance. And the hazard is a degree of poisonousness. You can class substances as hazardous and non-hazardous. It's just they all have some degree of hazardness. And this belongs to the substance. If the substance is gone, the hazardness for this substance is gone as well, obviously. And with hazards, there are 2 main distinctions that you look at. There's acute toxicity and chronic toxicity. And acute toxicity you will discover quite quickly. If you eat a spoonful of cyanide, then your lifespan will be very short. However, you could smoke a fair few cigarettes before your lifespan will be shortened by these cigarettes. And when we deal with food contact materials, then the probability of having an acute toxic effect is quite low. Otherwise, this would be noticed a lot sooner, and the regulation is not so relevant. That's why we always deal with chronic toxicity. And there are few chronic toxicity scenarios that are as hazardous as smoking. So it's very difficult to show this epidemiologically. So it's very difficult to take a set of people and say, you've been eating out of plastic, and that's why your lifespan is short. And we hear many times in my job that people live longer, therefore it can't be that bad. But it's also important to state that people live longer because medicine is progressed a lot. It's not because we are exposed to these substances that we're speaking about today. Then, to find out if a substance is risky or harmful, then the dose comes into play, and it's the second part of which constitutes the risk to chemical substances. And the question here is, how much is too much? So the hazardness of a substance defines how much of that substance is too much. Yeah, that's on substances. So let's look at food contact material. The number of substances we are looking at is staggeringly high. It's not millions and billions like the substances that exist or can exist within chemistry, but it's 100 to 1,000 times higher than the substances we are dealing with when we look at, say, pesticides, which are often in the public focus. So, it's this top line here. And then comes the toxicological evaluation. So with pesticides, we pretty much know exactly how toxic they are. We know from a lot of the metabolites how toxic they are. We know a lot about them. With food contact materials, we don't know much about many substances. We don't know what they are. We might know that they are there, but we don't know what they are. And this is a problem. And then, as I said before, the limits, what limits do we use to compare? And the dose that we get is also relevant. And also here we have a factor 100 to 1,000 times higher exposure to substances from food contact materials than we do to pesticides. So pesticides contamination of food is in the level of micrograms per kilogram, and with food contact materials it's milligrams per kilogram. And you may think a milligram is not much, but maybe it is. So if you say there's a medicine, a tranquilizer, Temesta, the clinical dose that is used is 1 milligram per day, and it works. So this can have an effect. If you take LSD, then you will be sky high for several days if you have a whole milligram of it. And if you take oral contraceptives, or the women who take oral contraceptives can prevent being pregnant for a whole month with 1 milligram of substance. So then comes the limit. And I just said, check it with the limit. And this is also one of the aspects where it's not always so easy. Sometimes it is. We have lists in legislation that show how much is allowed to come from your food contact material into your food. And there we can just check the value with the list, and that's it, and it's done easy. However, many substances don't have such a value in legislation, but people say they are unregulated, and this is also not true strictly, because the framework regulation, the basic principles for the control of food contact materials state that substances shall not migrate at levels that may endanger human health. And so we have to find which level this is for every substance in order to set a limit that we can effectively control. So analyze it. When we analyze substances, we generally separate them. So separation is at the basis of any analysis. And this is a very simple example. You may remember it from school. You have this is like a filter. People do this at school with filter paper and felt pens. And you can see that along this axis, these pens, the dyes in these pens are separated. And you can see that this colored pen and this colored pen have the same amount of the same dye in, but they also have other bits in, so to make different colors. Now, the separation is one thing, then we have to identify them and so on, but the separation also, you need to be powerful enough to separate. You see in this example, there are a few blotches. There's not space for many blotches in it, so we tend to use more sophisticated analytical tools than thin layer chromatography. And I can show you an example of such a tool. It's a two-dimensional gas chromatography. So in principle, this picture is nothing else but the picture that we saw before. The detector, instead of our eyes, is a different one, and then it's visualized so that our eyes can see it. The separation power is much bigger. You have much more space for dots on this plot. I don't want to disadvantage you on this side. So it's an extract from a polyolefin granulate. So these are little, like, I don't know, a bit like gravel, but a little bit smaller than gravel, and they're plastic beads, and they get formed into all sorts of food contact materials. They don't have many additives in them at this stage, and we took an extract of this granulate to analyze it, and we get criticism sometimes for extracting this granulate because it's not real, it's not what the consumer eats at the end. The reason we take an extract is, one, that we don't know what shape this material will finally take before it's in contact with food. So to do a migration experiment contains a lot of uncertainties. And secondly, the limit of detection is extremely crucial. If we take Article 3 and the thing that substances shall not endanger human health, then the lowest level where this may be an issue is very, very, very low. It's so low that analytical chemists struggle with this level, especially if you do a migration test. So if you do an extraction, you get more substance out, you can measure smaller impurities, and then you can figure out whether this could be an issue or could not be an issue in the final product. So this is why we do an extract. You see, this top section here has a lot of peaks. Each individual dot is an individual substance. And these peaks are all from oligomers. The top section here is polypropylene oligomers, and the bottom section is polyethylene oligomers, and they merge into each other because it's some copolymer. There is 1,000 milligrams per kilogram extractable oligomers in this granulate. And the toxicity of these granulates is being discussed now in the context of mineral oils because the structure and the properties of oligomers from polyolefins might be very similar to those of mineral oil. So the last word has not been spoken to the safety of these oligomers at all. But you also see in the bottom section here there are a lot of dots that are not oligomers, and we counted them. So we looked at dots that were there at concentrations higher than 1 milligram per kilogram in the plastic because we thought they could be relevant for the migration into food. And we know that there were more than 1 milligram per kilogram because we have this, it's a bit difficult to point, this spot here and one here are 1 milligram per kilogram internal standards. And there's one for 0.1 milligram per kilogram internal standards. And there are 9 substances that have a higher content than 1 milligram per kilogram. And there are 20 dots or substances that have a content that are between 0.1 milligram per kilogram and 1 milligram per kilogram. And 0.1 milligram per kilogram is the level that we have worked out that might be relevant when you make a food contact material. Because then it might migrate at a level that would expose a consumer to more than 0.15 micrograms of this substance per day. If you have a genotoxic substance, this is the threshold of toxicological concern that would count, and it is very, very low. But how do we know if this is a substance that is genotoxic or not? And the bottom line is we don't. We don't know what these substances are. We don't know what their structure is. And if we don't know what their structure is, there is no way we could ever determine what the properties, the toxicological properties of this substance is. So, anyway, get back to my initial job. I get a plastic, I analyze it, and then I can do things with it. So I can do the easy bit. This substance here, this big one, this green bit is a very big substance. This is an antioxidant, and we know what it is. We could identify it, so I could, in principle, find a food contact material that's produced with this granulate and then measure the level of this antioxidant that goes into the food, and then I could compare it to the list and see if it's good, if it complies or if it doesn't comply. And these big substances here, we also know they're monoglycerides. They're not very hazardous at all. But yeah, this substance here, I think the right one is the two that are very close together. And one of them is just unknown. We found no database hit, and we don't know what it is. So, yeah, it gets much more complicated. This is what I've just told you. There's another aspect here I would like to mention is that if you want to properly quantify and go into food and see what goes into food, then you generally, as analytical chemists, compare to a known value. So they need to have a pure substance. And these pure substances aren't even available for many of the substances that are regulated in the food contact material legislation from the EU, which in itself is a bit of an issue. So I would like to use the last 5 minutes to tell you about where this leaves us and where I think the future developments lie, because many of the people involved in food contact materials have jobs to do and have to do jobs better, including us, of course. So the use of fewer substances I always found is a very striking concept, and maybe someone from industry today will be able to tell us why this doesn't seem to happen. Because the Swiss government has got an ordinance on printing inks. And in this ordinance, they list 5,000 roughly, maybe it's a bit less now, 4,500 substances. And they say how much they're allowed to migrate into food. And in this list, they've got 80 substances that are photoinitiators. And photoinitiators have been one of the big scandal substances within food contact materials. But there are 80 different ones, approximately, in this list. And to me, as a non-industry person, it's completely ununderstandable why there need to be 80. Why can't there only be 4? And this would then also maybe enable a thorough risk assessment of these 4 substances. So, yeah, this is an open issue. This is something for industry to maybe think about. I'm sure they do think about it. Another point is the lack of the control of compliance work. So we, as an enforcement laboratory, we are faced with a food packaging material, and it contains printing inks with 5,000 substances that are regulated, plus the other ones that aren't regulated. It contains plastic with 1,000 substances that are regulated, plus those that are not regulated. It contains so many substances, it's impossible for us to measure them all and to quantify them all. So I think a way forward for enforcement for places like my workplace would be to focus more on checking the compliance work. That is, to ask the chain of manufacturers who are involved in a final food contact material to tell us what is in the food contact material and how they assess the safety of all the substances that may finally migrate into the food. The middle point is a biggie. It's something that is emerging, but I must tell you, I think it's still years from being applicable and practical. But it's a very striking concept. So you have these mixtures of substances that come from the food contact material into the food, and maybe, possibly, one way to assess them would be to use bioassays, to put the entire mixtures onto cells, specially prepared cells, and measure a biological response. However, there are some tests that, for instance, are fairly reliable for genotoxicity or for mutagenicity, but the sensitivity is very low. So if we have a mixture of, let's just say, 1,000 substances, then maybe the one that's genotoxic is there only at a tiny amount, but at such a high amount that it would be of concern. But because we put the whole mixture onto the cells, we can't get enough of it onto the cells to actually measure a response. And then there are other types of bioassays that are much, much more sensitive, but the meaning of these bioassays for the real life is not quite clear and still needs to be investigated a lot more. But the concept is really striking, and I think we also need to engage more with bioassays and how they could work. And for me, or from my point of view, it is always a gauging of how useful they could be, or if they could be useful at all. They might be, I don't know. Then the NIAS, I didn't introduce this acronym, but it's non-intentionally added substances. It's all these substances that are not regulated but end up in your food. And they are evaluated by ETHZ at the moment. If you apply for a substance, then you have to give a dossier and you have to say how you make it, and you have to show which impurities are in there, and you have to show that these impurities are safe. And ETHZ then looks at it and decides, yeah, that's good. And then the dossier disappears someplace in the cellars of ETHZ, and the substance that was applied for ends up in legislation. So there's a lot of work done that's of no use to anyone. So I reckon that also the legislator / the scientific committee or scientific institution of the legislator should make a list of evaluated NIAS so that it would be publicly available. And ultimately, every time I think about the future processes, I think that it might be the way forward, or the way that things will end out to be automatically, is by an FCM approval process, much like with medicines, where a company makes an FCM and then applies for it to be approved and gets patent protection for it or whatever. But this is even further in the future. So I thank you very much for your attention, and hope that you have a nice rest of the day.